I can't. Today, same thing as normal. I want to keep making through our review. I want to get through all of our units so that we can then maybe focus in on, hey, like this unit, I really don't know, so I can spend extra time on that. We can do, I really want to have you guys grade an FRQ, right? I'm going to give you maybe a student response, and I'm going to make you grade that FRQ so that you get some familiarity with how your FRQs are going to be graded when you take the test. But I want to keep going. We're almost done reviewing units. Today we're doing, sorry, my contact's been folded or something all day. We're on Unit 6. Does anybody remember Unit 6 by chance? We only have 2 units that we haven't reviewed. What topics haven't we talked about yet? Yeah, simple harmonic motion is Unit 6. What was the very last unit that we did this year? Torque. And then
circular motion.
Yes, good. That'll be Friday. We'll review. Then we'll have gone through and went back over each of the units. So then we can shift gears and again be thinking of ideas and input of what's going to be really useful for class time. I want some feedback and some advice of like what's truly going to be useful to you to help you improve and review in class. What can I do to help you? Whatever it is, I'm open to ideas. I got to get this thing queued up.
When we go for the test, we should study the physics of Mario Kart. Yeah. We can bring in some stuff and
I could
Mario Kart down. Could you endorse this idea?
I could see if I'm allowed to endorse such an idea.
Once the AP test is done, pretty much this class doesn't really have
well,
point.
That's not true.
Yeah.
I get what you're saying. The ultimate goal is that AP test.
Yeah.
So I get what you're saying. We still need to be learning something. I'm open to that idea. Absolutely. We just would need to formalize it and have something concrete that you can give me at the end of that experience that shows me you were learning something, applying physics.
You can say like...
Oh, right now. Put that on the back burner. You can think of that. I'm totally open to that idea. But until we got that AP test, let's stay focused on that. But just so you know, I'm not shutting that down. We'll keep that on the back burner. Today I want to review simple harmonic motion. This was... I don't know, how did you feel about this unit? Did you feel that when we talked about it, it's like, this is weird stuff? Or did you think it has a weird name, but it's stuff I kind of know what's going on?
I remember the least about it.
Okay, you remember the least?
Yeah.
Okay, so this might be one of the most useful reviews. Simple harmonic motion sounds fancy, sounds intimidating. It's really not. If you stop, break it down, it's just a very specific type of motion. Whoops. Guys, can we get phones away, please?
Yes, sir.
If you have this completely memorized and down pat, that's fine, but I don't think that's true for everyone. I can't imagine it is. That's not true for me. So I want you guys to at least pay attention and kind of get this back on your mind. Simple harmonic motion, so SHM, that's often the acronym since it's a big, long unit title. All it's describing is a very specific type of motion. That specific type of motion, it's repetitive. It oscillates. It goes in a cycle that repeats over and over and over again. It's either a back and forth motion, up and down motion, a combination of the two, rotation, a pendulum was another example, swinging back and forth. But it's a repetitive back and forth motion that travels the exact same path every time. A pendulum, it sits and goes back and forth on the same path. Right? If you attach something to a spring on a table, assume it's frictionless, and you squish it and then you let it go, it's going to start vibrating or oscillating back and forth. It's not moving, it's not changing direction, it's just moving back and forth in the same path. And even more specific, it returns to each position, velocity, and acceleration at distinct intervals of time. So if you look at the motion and you pause it at this point in its motion, the position, velocity, and acceleration are going to be the exact same as if you play and then pause it when it comes back. Now, the directions could be flipped because it's back and forth. It's oscillating. But these values are the exact same at specific points in the motion. Basically, what that means is it's a symmetric motion. It's not speeding up faster and faster and faster. It's constant. It's repetitive. It's cyclical. It's oscillatory. It's oscillating, right? All these are different ways to describe simple harmonic motion. This is your textbook definition. If a physicist wanted to determine if it truly is simple harmonic motion, these are the criteria it would have to meet. One of the best examples, this is a really good graphic, by the way. It's a mass spring system, right? If you take that spring and you got to squish it a little bit at first, and then if you let it go, it does its own thing, and it will do this simple harmonic motion infinitely, right? Assuming there's no friction, assuming ideal world. That's what we're going to assume when we do simple harmonic motion. But it repeats over and over and over again. It's back and forth. Notice, at this end, the force is the same. At that end, the position, it's the same every time it goes back to that spot. The acceleration, right in the middle, it's 0 every time it gets back to that position. So that's showing that position, velocity, acceleration, they repeat. Every time you come back to the same spot, these values are the same. Should make sense. It's repeating the same motion over and over. If you pause it at that point in time, it's repeating the same thing, so it's not going to be changing. Some of the questions to think through, okay, what's the point of this? How do I use this? One question is, when is the force on the spring the greatest? We go one by one. And again, the graphic is helping you. It's actually showing you. But I want you to be thinking about, why is that true? Brody, when is the force largest? So the block is at end. Is it any specific end? No. They're both the same. The direction's different. Right? Over here, my force is going to pull it back to the middle. Over here, my force is pulling it back to the middle. But Brody's right. At the very end, you have maximum force. Can someone tell me why you have maximum force? Yeah. At this end, not only is this spring compressed the most of any point in the motion, but the other spring is stretched. Springs do not like to be compressed or stretched. They want to be at their resting length. So at the end, this compressed spring is trying to shove it the other way. On this end, that stretched spring is trying to pull it back. That's why your force is maximum. What kind of force do you have in the middle? It's quick, but right there. What do you have right in the very middle of the motion? What kind of force do you have? You have nothing. That is the equilibrium point, the resting point. That would be if I put the block right in the middle and I let it go, it's just going to sit there. The springs aren't compressed or stretched. It's just chilling. Okay? What about velocity? When do you have the most velocity? Where is it moving the fastest? Right in the middle. Again, the graphic helps you out a lot. It literally labels all the vectors for you. But think about it, right? Watch the block. Where is it moving fastest? It's definitely not the ends. The ends, it slows down and actually stops before it starts to speed back up. Right in the middle is where you have maximum speed. How about acceleration? Where is the greatest change of speed happening? At the end. Does that make sense? At the end, the whole thing, both springs are trying to shove it the other direction. Also, notice that force and acceleration are always the same size and the same direction. Can someone tell me, using physics, why that is? Why are force and acceleration always paired together? Yeah. Do you have remember the equation that directly relates? F equals ma. He said force and acceleration, the force determines acceleration. He's exactly right. F equals ma. If I have a force in this direction, that's the acceleration. You see that is still true. We didn't break physics with simple harmonic motion. Newton was still right. That's still true. This was a trick question. When is the force and acceleration in opposite directions? The answer is never, because Brody just told us. They're always in the same direction. And Newton's second law says that that's always true. Velocity and acceleration. When are those two in the same direction? Huh? Okay, so right here?
To the middle.
Yeah, to the middle. So from the end of the motion until the middle, velocity and acceleration are in the same direction, then they switch. So it's only when it comes from the end towards the middle that that's true. Think about it. Going this direction, the block is actually, it's moving this way, but it's slowing down. That's why acceleration is going this way. It's slowing down. When it gets to zero, the velocity switches. Acceleration is still going this way, but then it speeds it up. As soon as it passes the midpoint, the force switches. So the force slows it down, it stops, and then both your acceleration and velocity come back to the middle. And then you repeat. Huh? Can we? Freaking I. We could. If we got the air track, though, the air track it simulates frictionless. I don't know if we have big springs.
I'm just going to take it off of someone's suspension.
You think it would oscillate?
You gotta find one of those lifted trucks.
There's only one way. Yeah, there's about 4 or 5 of them that park over in the corner of the parking lot because they think they're cool. And I think we should just take the suspension off of them.
Oh my gosh. I think we forget the stiffness of a vehicle spring.
Exactly. It would be. That's why Brody would have to operate it.
I mean, you're talking like 1,000 pounds to compress it a couple inches.
Listen, Brody, lift a total pounds, but that's a lot of weight.
Yeah, no, car springs won't work. You would need a really flexible. The less stiff your spring is, the more motion you would see.
You could just. What about the ones like the doors? Like
yeah, slinkies would work.
Or the screen doors. That's what I'm talking about.
You could, yeah. It'd just be hard to get the frictionless part. The air track would solve that, but then you're restricted to just the track length.
Yeah.
And I don't. I have some springs, but they're little.
Perfect. I was going to say the one that.
We could try it. Anyway, I want to keep getting through review. So the other part of simple harmonic motion is this oscillation idea, this repetitiveness. When you have simple harmonic motion, no matter if it's going linearly or, again, a pendulum is rotating, that's a curved or circular motion, either way, you have oscillations. You have a cycle that repeats over and over. So you can use circular motion. measure of how much rotation you have per time is omega. That's how fast it's oscillating or cycling. You guys remember what capital T was? This equation is telling you that the speed is equal to one rotation divided by the time for one rotation. This is not a little t. It's not just time. It's a specific quantity of time. Period. Period is a length of time that specifically is how long for one complete rotation or oscillation or cycle. So go back here. All right, I'm going to start timing. 1, 1,000, 2, 1,000, 3, 1,000, 4. 4 seconds is the time it takes for this object to complete one cycle. That is what capital T period equals. Period is one complete rotation or cycle divided by however fast it's spinning or cycling. The inverse of period, which is time per cycle, is 1 over the frequency. What does the frequency mean? Yeah, it's cycles per second. Hertz. Did you guys know your Wi-Fi uses hertz? You guys know you have 2.4 and 5 gigahertz? That's the frequency of your Wi-Fi signal. A gigahertz is 1, is it billion?
Sure, you can say that.
I think giga is 10 to the 9th. You'd have to check me, but a gigahertz is like, say, 1 billion times per second. That's how fast that frequency goes. You guys know that your radio works on frequencies? Right?
1 billion.
1 billion, yeah. So a gigahertz is a billion cycles in a single second. That's what your Wi-Fi is doing.
What's a good gigahertz for Wi-Fi?
The higher the gigahertz, the better your Wi-Fi is. Because it's cycling more, it's got more information, it's faster per second. I disagree. The school's Wi-Fi is incredible, right? You're having to provide Wi-Fi for 30 people at the same time. Minimum.
A lot more than 30.
Huh?
I guarantee it's a lot more than 30.
Well, that's what I'm saying.
At least 500.
The Wi-Fi is very good, but you're using so many devices, you can't all get maximum capacity. So don't hate on the school Wi-Fi that much. It's really good.
I go home and check my Wi-Fi.
Yeah, you can do your Wi-Fi
When
speeds.
everybody leaves and I stay and I go into Arms' room and we do esports stuff,
Yeah,
the Wi-Fi is insane. It's gone.
yeah. The school's Wi-Fi is very good. If you only have a couple devices on it, you can get full traffic or access, essentially, to what the Wi-Fi can offer. Yes. Anyway, frequency is how many cycles happen in 1 second. Okay? Period is how much time it takes for just one cycle. They're inversely related. Right? Angular speed is cycles or radians per 1 cycle. 1 rotation per cycle, cycles per second. That's the unit for frequency. How many times can you oscillate in a single second? Did you survive your AP test? Did you survive it? Was it bad? Not really? Well, that's good.
Please tell me your score.
No. Just how was it? This is an interesting concept. This shows you how, even if something is linear, it involves oscillation or circular motion. You can use oscillation equations to determine linear position if it's harmonic motion. It's moving in a cycle. Well, that cycle repeats itself. So this reference circle is saying, if my object, I'm going in a circle, right? I can determine linear position. I can relate the two. Or if I have a mass spring system that's moving back and forth, the position on my circle follows my linear movement. Right? You don't need to know. Oh, it does it for me. Do you see this? You guys see the connection? This is our mass spring system. It's oscillating linearly. You're like, well, linear isn't rotation. It's not. But because it's harmonic motion, it's repetitive, there's a cycle to it. There's a repetition, a revolution. So you can match the position with rotation around a circle. This connection between linear and oscillation is why you can evaluate linear position by a rotational equation. This is in a linear position of any object in simple harmonic motion. Again, this is circular motion. Do you know calculus, right? This is a wave function. So up and down, up and down. At any point in a cycle, that position, speed, everything's the same. But it repeats. So as long as I know what point of the oscillation it's at, I can tell you how fast it's going, where the position is. What I need to know is the frequency. If I could figure out the frequency of simple harmonic motion, I could plug it in and determine position at any moment in time. That's one of your equations on your equation sheet too. You'll be able to use that. This A stands for maximum position. You can't go bigger than the end of the spring, so to speak. So this, when this is 1, you're at maximum. You're either on this end or you're on this end. Oh, my contact. So if we look here, I have a question. I got a mass spring system. 2 springs, just like you saw, it's going to oscillate back and forth. I want to know, I know K, I know the mass. I want to know the speed when it's at 4 centimeters. At this position on the graph, how fast is it moving? This is where we're going to bring back what we talked about with energy. Right? When you set this thing in motion, the energy is being transferred from spring potential energy that gets released and creates motion, which is kinetic energy. At any point in time, all of my kinetic energy plus all of my spring potential energy cannot be greater than the maximum kinetic energy. This would be your system energy. This is, if you take the spring and put it at its largest amplitude, furthest away, that is maximum energy. It's all spring. If you let it go, you'll lose spring as it picks up speed, and then it slows itself down as it stores spring energy. You release the spring energy and it picks up speed, and then it slows down. At any point in time, motion energy and stored energy cannot exceed the total. So we can use that to our advantage. I actually want to take a second trying to find this. Right? So, first of all, I need to find what is my maximum energy of the system. That would be right here. I need to know my spring, total spring energy. 1/2 K A squared. What's my spring constant, K? Right in the problem. 15 Newton meters. That's the stiffness of my spring. What is the amplitude? Look at the very center of the box. What is the amplitude of this motion? Do we need to remind ourselves what amplitude means? I see why you said that. But remember, where is this box located at 0? Isn't the middle of the box right at 0?
Yeah.
So I want to watch the middle of that box. Where's the middle of that box? At the limit. Because Ethan, I'm assuming you said 10. That's the largest distance, right?
Oh, okay, 9.
What I'm saying is we gotta be careful because we're not traveling watching the right side of the box.
Yeah.
We want the middle of that box. Where is the middle of that motion go? So it's actually 9. Amplitude is largest displacement. The limit of its motion, how far is that? This is, I shouldn't use 9. That's centimeters. I don't want to measure distance in centimeters. I want meters. What?
0.09.
Yes, 0.9, right? 2 decimal places, yes. Okay? This is how much, anybody have a calculator? Oh, I guess I got mine handy. 0.5 times 15 times 0.09 times 0.09. That is my total energy. At any point in time, my object cannot have more energy than this. What I was asked to find is how fast is it going when it's at 4 centimeters, right here. So what I need to do is say, okay, any kinetic energy, 1/2 mv squared, plus any spring energy has to be equal to this total, this limit. What's my mass? 0.25. I don't know V. All right? One-half. What's my K value for the spring? We already said it. Trevor told us earlier. I think I heard it. 15 Newton meters. Question literally tells us the K value for the spring is that. I'm looking at the position of 4 centimeters. So that is going to be my position. So I'm going to put, again, 0.04 squared. That has to equal the total. Do you see how I've made an algebra equation with literally one unknown? You're just going to do algebra. Figure out what this is, subtract it over, divide by 0.125 over, take the square root, you have velocity. Right? This would be a good, like an FRQ question. There's going to be more to it. They want to see, do you understand simple harmonic motion? Do you get that movement and spring energy? Those are the only types of energy you have. And they're going to equal the total, no matter where it's at in the motion. And do you remember conservation of energy? Do you remember that the 2 types of energy possible always add up to whatever the total is? There's no energy coming in or out. So you know this is going to be constant. Right? You can't just do a, momentum problem. Like on FRQs, I mean. That's almost never going to be the case. They're really going to test you and say, can you combine 2 different concepts together? Does this process or this kind of example problem make sense? we remember kinetic energy, right? 1/2 mv squared. This is a little bit new. This is spring energy. It's stored energy in the spring because you compress it or stretch it. It doesn't like that. It's waiting to be released, and then it will create motion. It will release the energy. Those are the only two types, so they're always going to add up to the total. If you want to know, well, what's the total energy for the system? How can I determine that? Imagine this object has maximum energy when it has maximum displacement. All the energy is stored in the spring. So I could figure that out, and then that is my total. Simple harmonic motion really focuses on two versions or types of simple harmonic motion. You guys remember the two? What are the main types of simple harmonic motion we talked about a lot? Springs and pendulums. Those are the two. If you attach a block or mass to a spring and compress it and then let it go, that is, I think what we're doing here, yes, spring mass system. The other one was a pendulum. You got a hanging mass and you lift it and then you let it go. So right here, you don't need to know how this comes up. It's on your equation sheet. You need to realize that this is the period, the time for one rotation or oscillation of a spring mass system. What are the only two things that affect the period of a spring mass system? Should be an easy question because the equation is staring you in the face. Mass affects the period. That's correct. What else affects the period?
The spring constant.
Good. Spring constant. Right? Use this equation to tell yourself the only time the period is going to change is if I change the mass or the spring constant. If I have a spring mass system and one time I pull it a little bit and I let it go and time how long it takes for a full cycle, I now do the same thing and I yank it as far as I possibly can and let it go. Which one is going to complete a full cycle faster? You sure? One time I have a spring mass system and I pull it a little bit and let it go and it starts to oscillate and I time how long for one cycle, the period.
Okay.
I do the exact same thing with the exact same object, but I pull it really far and I let it go and I time how long it takes for it to go back and forth once. Which one completes a cycle faster? They're the same. It doesn't matter how much you pull it or how little you pull it. If you keep the mass and the spring the same, the period will always be the same. It's a little counterintuitive. Even if you forget that, your equation is staring you in the face. If none of these variables change, and the question's like, hey, compare the period from this situation to this one, and you're like, wait a minute, the mass is still the same in both of them, and it's the same spring. You don't have to do any work. Just say the period is the same in both, because mass or spring constant don't change. Don't forget to use that equation to your benefit. The other one was a pendulum. You have a mass hanging by a string, and you lift it, and then you let it start swinging. A grandfather clock. That's a pendulum. It's simple harmonic motion. It's a cycle that repeats itself over and over and over. The equation for how long a pendulum takes to complete one cycle, that's a period, T. The only two things that affect a period or a pendulum's period is the length of the string and how strong gravity is. So for any pendulum on Earth, what is the only variable that changes the period? Nope. Pendulums and spring Mass spring systems, they're different. They have different equations. Pendulums only are impacted by how strong gravity is, which on Earth will always be the same, and the length of the string. I showed you the example of Walter Lewin, the professor. He's got a bowling ball on a string, right? He pulls it really high and then lets it go. And he times how long a period was. And then he takes it and he pulls it just a little bit and he lets it go. They had the exact same period. Makes sense, right? Amplitude, or, how high you lifted initially, it's not in the equation. It literally is irrelevant. He also changed the mass. He had it, he was swinging, and he had them time. What's the time for one complete rotation? Down and back time. Then he literally sat on it and timed himself again. Right? He added tons of mass, did the same thing. The period was exactly the same. It doesn't matter how heavy the pendulum is. It literally only matters how long the string is, assuming you stay on Earth. They might ask you a trick question. You take this pendulum and you go to the moon. How does the period change? Think that through. Will it take longer to oscillate if I go to the moon, or will it oscillate faster if I take that pendulum to the moon? Is gravity going to go up or down?
Gravity's going to go down.
Gravity's going to go down.
The number's going to be larger.
What happens if gravity, the denominator, gets smaller? What happens to the overall number?
Gets bigger.
Gets bigger, right? 1 divided by 2 is bigger than 1 divided by 10.
Very true.
So then if this gets smaller, the whole thing gets bigger, period goes up. Your pendulum is going to swing slower on the moon because there's less gravity to oscillate it. They'll probably ask you trick questions, or say a made-up planet has 1/8 the gravity of the moon or the Earth. How does it affect the period? Right? You'd plug in an 8. I don't know. Say it's a fourth. The square root of 1 over 1/4. Well, 1 over 1/4 is what? 4, right? What's the square root of 4? 2. So your whole answer is going to be times 2. Period would double. They're going to test if you know these equations and how to use them for a spring mass system and a pendulum. They're on your equation sheet. It's right there. You just got to remember what the variables are and think through how they affect. Spring mass systems and pendulums are the main focus of simple harmonic motion. Those are the 2 examples that we talk about in this class. That's why they're having equations for just those 2 scenarios. You guys have any questions on simple harmonic motion? Anything on your equation sheet? No? Anything I explained a second time that didn't make sense? Okay, so you guys, I think I posted it. I hope I did. I'm going to give you, and I think it's a good one that I found. It's from a very recent. I think it was from the 2018 or 2019 AP test. So it's a very relevant FRQ. I tried to get the most recent one I could possibly find. This Unit 6. So again, if you're a virtual student, I have this attached that I want you to try this. Right? And then I'm also going to attach the answer key once we're done. That way, if you want to go home and look over this again, right, you can try to grade yourself. What would I get if I turn this in on my test? I'll give you the grading rubric that us teachers. Do you know AP teachers are the ones grading your actual AP tests? Like, you sign up and you literally go and you spend, I think it's like a week straight, and all you do is grade AP FRQs.
Are you doing it?
No. I want to eventually, because I think that would be really useful to get lots and lots of practice of this is exactly what AP expects. This is exactly what is okay and not okay for this type of question. I would learn a lot that I could help teach even better. but it also is a little.
Speaker knows it.
Yeah, you can sign up to be a reader, it's called, which is essentially a grader. It also sounds brutal. Grading is awful.
You get paid for
I think you do. I'm not sure how much.
it. You do.
You do?
It's so much
Okay. So that'd be worth it, but it's grading sucks. It's the worst part of teaching, I think. Takes a long time. But anyway, I'm going to give you this simple harmonic FRQ. Once we get through that, I got done quick enough that the rest of the class is going to be work time. If you want to ask me questions, if you want to start doing, again, same homework as I always do, I want you to go take that workbook and just pick 10 multiple choice on simple harmonic motion and try them out. Please try the problem and grade yourself. The answers are in that workbook. So when you turn in your homework, I want to see your answers and then your grading and corrected work. And if you could, give me like what you did wrong or redo the problem now that you know the answer. Because then I can see, okay, they did the problems, got half of them wrong, but they went back and redid the ones they missed. So they kind of figured out how to do them correctly, what they did wrong. That's what I'm looking for. So again, I'll stop this. I'll give you again the 13 minutes. This is a legit AP question. So this is exactly what you would see on the test. This question is 7 points. You should spend about 13 minutes to be on pace. So we'll do that in the 13 minutes, and then I can show you the grading rubric. Like, hey, part A, you would get a point for the right answer and this equation. So you can get some feedback of, oh crap, I would have missed that part because I, didn't put my reasoning. Or, oh crap, I didn't show my work. That's why I didn't get points there. I want you to start to get a feel for what kind